Hello everyone, welcome to another kinetic tutoring video. Today we're going to be switching topics really. I know my last couple videos have been focused on torque, rotational motion, and now we're going to be moving on to our next unit, which is going to be restoring forces, oscillations, and pendulums and spring forces. So yeah, without further ado, let's get into the problem. Alright, the prompt reads, starting with the restoring force, derive the period of the simple pendulum. So let's take a look at our diagram here. We have a pendulum, it's swinging back and forth, and we want to find the period, which is how long it takes for it to swing this way and then swing back. So it's telling us to start with the restoring force. Since we have a rotational force here, we're going to set that up in terms of torque. Our net torque equation is going to be I alpha is equal to the gravitational force, which is the only torque being applied. We see here that this vector that's causing the pendulum to oscillate is going to be mg sine theta. And we know that torque is simply force times radius. We can see here that the force is being applied at the end since it's a simple pendulum, so you can write the radius as L. Now we want to get our alpha here on its own, so what we're going to do is divide both sides by inertia, and since we have a point mass here, we know that the inertia of a point mass is simply ml squared, so we can rewrite inertia as ml squared on the other side in the denominator. From here we can cancel out some terms, get rid of 1L, get rid of the m's, and we'll get that alpha is g sine theta over L. And since we have a small angle of theta here, we can just approximate that sine theta is going to be somewhat near the angle theta, so we can just rewrite this as g over L times theta. Now, in order to find our period, we want to find our omega, and this can be done by using the displacement equation of this simple pendulum. So, since it's starting at a displaced position, we know that it's going to be at its maximum displacement, and our angular displacement is going to be theta in terms of time. And let's write the basic equation for our displacement, and that's going to be a cosine parentheses omega t, where omega is our period. And so the reason that we have cosine here and not sine is because it's starting at a displacement. So if our oscillation was to begin here, then we could rewrite this as a cosine omega t. But since it's starting at maximum displacement, we have to write it at cosine t omega t, because at time 0, cosine is going to be equal to 1. So our displacement is going to be equal to a. Alright, so from here we want to find another equation for alpha, and the way we're going to do this is by taking two derivatives of this equation right here. So let's just do that. Our first derivative is going to be omega t is equal to a sine omega t. There's going to be a negative up front, negative a sine omega t times the derivative of the inside, which is just going to be omega. Now let's take another derivative of this in order to get our alpha. Alpha of t is going to be negative a cosine omega t times the derivative of this again, which will be omega multiplied by the omega we got last time, which will give us omega squared. Now that we have our alpha, alpha is equal to negative a cosine omega t times omega squared. We notice that this term is a term we've seen before. We can see that this is our theta right here, a cosine omega t. So we could just replace that with our displacement, and we will get that alpha is equal to negative a, or sorry, there's no a there, that gets replaced too. It's going to be negative omega squared times displacement. Now we could set these equal to each other. We have our g over L theta and our negative omega squared theta. G over L is going to give us omega squared since the thetas cancel out. So our omega is going to be square root of g over L. And you might have noticed here that I just got rid of the negative. That's because since it's oscillating, the direction doesn't really matter too much because it's just going to be going back and forth. So there's no like real constant direction that's going to keep going in. So now that we have our omega, which is going to be root g over L, we can plug that into our period equation, and our period equation is t is equal to 2 pi over omega. So we're going to take 2 pi, multiply it by 1 over omega to get our t. 1 over omega is going to be simply this flipped, so we will get our final period to be 2 pi root L over g. I hope this helped, and make sure to tune in later for more physics tutorials, and that's all I have for you guys today.